Dear Rector, Professor Phil and McKean, Honorable Dean, Dr. Pulu Wardati, dear Professor Lutfi, dear Professor Dian, dear committee members of the conference, distinguished researchers and academicians, ladies and gentlemen, it's my pleasure and honor to be for the second year in a row part of this wonderful conference. Though this year, due to the pandemic, we are far apart from literally different parts of the world, maybe as far apart as it can be, but yet our hearts are there. I'm still haunted with the hospitality and the wonderful memories I had from the last year, and I'm looking forward and hoping that this pandemic will end as soon as possible. So maybe in other opportunities, maybe in one of the upcoming conferences, we will still be together physically there in Yogyakarta, so we can discuss and have those pleasant and wonderful conversations about the recent breakthroughs in science and the advances in engineering. Without taking your time, your valuable time, I'll continue with my talk. I'm going to share my screen. Okay. I'm going to share basically my presentation. Hopefully you can see it. My topic for today is going to be homomorphic encryption and its application in modern day world. I've divided my speech in five parts. I'll start with the introduction scope of the problem. Then we'll continue with some hard mathematical problems upon which modern cryptosystems are built on. Then we will see how homomorphic encryption works and how it looks like. In order to do, after doing that, we will see the modern applications of the homomorphic encryption. And finally, we are going to conclude our talk. So let's start with the introduction and scope of the problem. Today, we have around 30 billion devices connected to the internet. It's an estimated number. And all of those combined transmit or make data, which is around 44 zettabytes in 2020. Those data is being collected or transmitted from different research labs or banks or hospitals or even from private individuals. And so the data that they collect are data like genome sequences from, let's say, bio-research labs. Banks collect financial records such as transactions, credit card numbers, etc. Hospitals collect health records, which are regulated by privacy laws. So those are very sensitive data, very private data, but those data, if they're used in a proper way, can be very beneficial. For instance, genome sequences, if we have multiple or a lot of or enough of genome sequences of multiple individuals, of humans, maybe we can figure out something about the pandemic that is going on. Or if we have enough of data financial records, maybe we can figure out some credit card frauds or tax evasion and so on. Or if we collect enough of data from different patients by hospitals, then maybe we can come up with some patterns about certain diseases. But the problem is that all of those data are private and no one is willing to share it with the others. So that's why very often when those entities collect those data, they want to share it. They actually want to keep it in a safe way, and they do it by uploading it on cloud, such as Google, Amazon, or Apple. But because they have virtually unlimited amount of storage for low cost, and it's supposed that they are managed by IT security experts. But is it so? Well, I'm just showing you some recent headlines about attacks on famous companies, IT systems of famous companies like Google, which were millions of emails were hacked, or Facebook, or Yahoo, or Adobe, or Sony. So the problem is that even if those entities upload those data, sensitive data, to cloud servers, and even though those top companies hire leading cybersecurity experts, yet data breaches happen. Hackings happen due to new sophisticated cyberattacks, or even due to rogue inside workers, which are workers that work for those companies and maybe for some financial benefits, steal the data and give those data to other unauthorized parties. So what will be the solution to this problem? It's encryption. Since there are plenty of researchers out there that are not aware or not accustomed with what encryption is, briefly, let me explain that encryption is the process of translating or encoding, converting, hiding an information from its original form into an alternate, unrecognizable form. So if we have a message which might be financial data, health records, or genomes, or whatever, and it's private, we can somehow encrypt it or encode it and convert it in a garbled way so it cannot be recognized. We have an example for that, and so let's say that we have our original message, UN Sunan Kalijaga, and we want to encrypt it. We want this to keep it private. The encryption works usually with key, which is kind of a password, and the password for me would be ICSE 4. Okay, and there is a tool. Maybe I should share the screen again. Okay, I'm not sure whether you can see it. Okay, so this is what happened. If I have an input text, which is my message that I want to keep private, and this is my key, when I want to encrypt it, this is what I'll get. So this is the message that I get if I encrypt Sunan Kalijaga. Okay, and it's converted in hexadecimal. So basically, those are the same. Computers understand binary bits, and this is for the human beings. Now, if I just copy this part here, so I encrypted it. Now, let me put it over here. And now let me use the same key again, and I'm going to decrypt it. So this is my encrypted message, and you see you cannot learn anything from it. But if I have the key, I can decrypt it, and when I decrypt it, I get the original message again. So this is what encryption is about. Maybe I should go back now again to sharing the presentation. Okay. So, Sunan Kalijaga is my plain text or original message, and this garbled text is my ciphertext, and my key is the password is my key. Mathematically, we write this encryption in the following way. So if the message M is Sunan Kalijaga, then encrypting message M with key is written in this form, gives me a ciphertext. Basically, if I encrypt UIN Sunan Kalijaga with this key, I'll get this ciphertext over here. This is the message, the key, and the ciphertext. And the opposite, if I decrypt the ciphertext, I get the original message, which is this one. Basically, if I have a message, this is illustrated in this figure. So it looks like everything is fine, right? Because I encrypted everything, I upload it to the cloud. Even if someone breaks the system, I'm fine. But the problem is not solved. And we'll see why. So in order to see what's going on and what was the problem with this kind of encryption, let me go very briefly through some mathematics, through some stuff which is related to computer science. So computers, as you might know, understand the language of binary bits, which is binary digits or bits. And what is a bit? Well, it's a number, it's 0 or 1. This is what computers understand, nothing else. With n bits, we can represent 2 to the power of n combinations or numbers. Why so? Since 1 bit can be 0 or 1, that means that one bit gives me 2 combinations. So if we have n bits, that means that I have 2 to the power of n combinations. In this sense, how the numbers are understood by the computer is given over here. 0 is written as 0, 0, 0, 1 is 0, 0, 1, 2. Now we don't have other thing else other than 0 and 1. That's why we go with 0, 1, 0, 3 is 0, 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 6 is 1, 1, 0, and 7 is 1, 1, 1. As you see here, we have in total 8 numbers. And we do this with 3 digits, okay? With 3 bits actually. So 2 to the power 3 is 8. In similar manner, if we represent the numbers from 0 to 15, which are 4 bits, we only need 4 bits. Basically, from 0 to 15, we have 16 combinations. So 2 to the power of 4 is 16. Now, why did I mention that? Well, the problem that someone might ask is the following. If I have a ciphertext, this garbled message, can I break it? Can I retrieve the plain text from it? Well, let's see. What do I mean by attacking or breaking an encryption system? One definition by breaking a cryptosystem or a ciphertext is if we have the key. So if I have the key, basically I can decrypt and encrypt whatever I want. But is it hard to find the key? Okay. So it depends on the encryption algorithm and the key size. For the algorithm that I just used, which is AES, Advanced Encryption Standard, we have 3 key lengths. One is 128 bits, the other is 122 bits, and the other is 256 bits. So the weakest AES security is 128 bits. Since there is no known attack for AES rather than brute force, and brute force meaning I'm just checking all of the 128 bits combination one by one. So you might be confused. I use as my key ICSE4, but the computer actually converted it into bits, binary bits. And if it's not 128, it just appends extra bits. So what does brute force mean? It means to try all of the combinations of 128 bits, one by one. And how many combinations we have? Well, it's 2 to the power 128 combinations. But how feasible or doable and effective is that? Can we do that? Let's check. Let's see. Let's assume that we have a processor that has 1 hertz of computing power. And 1 hertz, we have a processor that has 5 gigahertz, and 1 hertz tries 1 key. So if our processor is a single core and it has a frequency of 5 gigahertz, and 5 gigahertz is 2 to the power of 30 hertz, that means that I'm checking 2 to the power of 30 key combinations per second. Let's see per year, how much is that? Well, per year, 1 year has 365 days, this much hours, and this much seconds, which is actually approximately 2 to the power of 25 seconds. So if in 1 second I'm checking 2 to the power of 30 keys, then in 1 year, which has 2 to the power of 25 seconds, how many keys I'm checking? Well, I'm just multiplying them, so I'm checking 2 to the power of 555 key combination checks per year. Then for 128-bit size for the key, we will need the number of combinations that 128-bit is 2 to the power of 1 divided by 2 to the power of 55. And this is 2 to the power of 73, 2 to the power of 73 years. Well, how much is that? We're not computers, we're human beings. We're using the decimal system to the power of 73, so approximately 10 to the power of 21, which is 1 followed by 21 zeros. And how much is 10 to the power of 21? Or 1 zeros following 1 zeros. It's called sextillion. And since we don't have a clue that we never use, I just want to compare this number with the age of our universe. So the universe is old 3.8 billions of years, which is approximately 1.3 with 10 zeros. So you will need much more time in the universe to break this. Of course, you might argue that I might have a computer, multiple cores, supercomputers, etc. But it's shown that even if you have supercomputers, you will still need like millions of years to break it. So we're on the safe side. encrypt your data, put it to the context, and we are done with the security. But is everything solved? Unfortunately not. While we keep the security, while the privacy of data, the problem is that we cannot retrieve information for data. We cannot use it for our own benefit. So basically, if we encrypt it, we cannot process the data. The solution is homomorphic encryption. Homomorphic encryption is a kind of encryption that allows us to make some processing, some operations of the data while it's encrypted. We will see in a while how it works. And in order to see some homomorphic encryption schemes, we will briefly go through some simplified definitions. So, maybe we know them from high school. What is a prime number? It's a number that is divisible only with 1 and itself. So 2, 3, 5, 7, 11, 13, and so on are prime numbers because they can only be divided with 1 and with itself. What is modulo operator? Well, modulo operator with modules and is basically, so I'll just give an example. 17 modulo 5 is 2. Why? Because if I divide 17 with 5, the remainder that I get is 2. So 17 divided by 5 is 3. And the remainder is 2. So modulo basically gives the remainder. That's why we can write it in another way. 17, we say it's congruent to 2 modulo 5. Why? Because if I divide 17 by 5, the remainder is 2. There is a whole branch of mathematics that deals with such operators, with modulo operators, called modular arithmetic. But yeah, in this module, there's something which is called a multiplicative inverse. Very simply, what is multiplicative inverse? Multiplicative inverse of a number, it's another number that when multiplied with the first number gives us remainder of 1. For instance, if I have 5, 5 multiplied by 4 is 20. And 20 modulo 19, because if I divide 20 with 19, the remainder is going to be 1. So that means that 5 is multiplicative inverse of 4, and 4 is multiplicative inverse of 5. Okay, so when we multiply the multiplicative inverse of a number with that number, I always get 1. Now let's go with some hard mathematical problems. I'll just briefly mention a couple of them, few of them. One of them is a factorization problem. What is factorization problem? If I have a number A, which is a very big number, which is consisted of more than 124 bits, like 124, 2000 or 4000 bits, and another prime number B, then if I multiply those two numbers A and B, I'll get N. So A and B are prime, big prime numbers, and N is the multiplication. Factorization problems tells us that to factor to find if I have only N, and I'm sure I know that N is multiplication of two prime numbers, which are huge. The finding those two prime numbers, it's a hard problem. So just imagine if 128 bits took 2 to the power 73 years, or 1 followed by 10, 1 followed by 21 zeros. Just imagine how much this would take. A lot of time. Another problem is this discrete logarithm problem, which is the following. I take a number A, huge number, then I put it to the power of x and find the modulo n of that number, which is b. If I give A, n, and b to someone else and ask him to find this x, the power, then this is called the logarithm problem. It's a hard problem. It is as hard as the factorization problem. So this is how it works. Basically, I have 3 to the power of x modulo 19. And if I say, okay, 3 to the power of 1 modulo 19 is 13. 3 to the power of 2 modulo 19, the remainder is 17, and so on. So the discrete logarithm problem basically gives you 13, the base of the logarithm, the modulo 19, and the results. And your job is to find the power. But of course, those are small numbers just for illustration purposes, and usually those powers are several hundreds of bits. If you have questions, maybe you can ask later on during the Q&A session. We have other hard mathematical problems. Well, I'm just going to mention the ring LWE. I'm not going to explain it in detail, but I'm just going to tell you that Unlike the others, elGamal, which is a recent hard mathematical problem, is even unbreakable on the quantum computers. That's why elGamal schemes are called post-quantum cryptographic schemes. Now that we know it, we have seen the hard mathematical problems, we can go and see how homomorphic encryption works, how we can encrypt data, and how we can process them. Okay, before going to that, we're just going to see another concept in cryptography, which is symmetric cryptosystem. Well, it's better explained with those two illustrations. Symmetric cryptosystem is a system that both the encryption and the decryption keys are the same. It's the same like the AES that we saw. Okay, so if I have the plain text hello encrypted and I get the ciphertext, I can decrypt it with the same key. But the public key cryptosystem, in the public key cryptosystem, we have a couple of keys. One is the private, and the other one is the public. The public key is public for everyone that is interested to have it, to access it, and the private key is kept private by the owner. So if I have the message hello, and if I encrypt it, let's say with the private key, I get the ciphertext, and I can decrypt it with the public key and get the original message, and vice versa. If I have the original message and encrypt it with the private key, and I get the ciphertext, then I can decrypt it with the public key. So if I encrypt it with the public key, I can decrypt it with the private. And if I encrypt it with the private key, I can get the original message, decrypting it with the other key. Decrypt with one and decrypt with the other. Okay, well, I'm going to show only one crypto system, how it works. Maybe the easiest one, just to have an intuition how it works. It's the elGamal crypto system. So key generation, let's see how we generate keys, how the keys look like, the public and the secret key. First of all, I'm choosing a huge modulus Q. Okay, so that the modulus that I just mentioned, which is something greater than 124 bits. Usually it's 2048 nowadays. After that, I choose a random integer x and g, two integers, from 1 up until q minus 1. Okay, and then compute age. Age is computed as g to the power of x modulo q. And then I have the public key. The public key is a tuple q, so the modulus, g, this random number, and age. And age is g raised to the power of x modulo q. And the secret key is x. I make the public key public so everyone can access it, and the secret key is secret. I keep it for myself. Now, if you see, h is g to the power of x. So basically, due to the hardness of discrete logarithm problem, I cannot find x, because if I find x, I find the secret key and the crypto system is broken. Okay, but discrete logarithm is hard. That's why we can do it. So this is the key generation. Now let's see how I encrypt the data. Let's assume that I have a message m. In order to encrypt the message m, I randomly choose y from 1 up until q minus 1, and then compute this term, h to the power of y. So h is public, so this h, I raise it to the power of y modulo q, and assign it to x. Then compute c1 as this one, g to the power of y modulo q, and c2 as the message m multiplied by this s. Then the ciphertext that encrypts the message m is the tuple of this one. The ciphertext is consisting of two parts, c1 and c2, and this is shown over here. So c1 is this one, c2 is this one. Now, how can I decrypt it? Well, if I have the ciphertext, in order to decrypt it, I'm using the secret key now. You see, here I use the private key like G, H, okay? And in order to decrypt it, I'm using the secret key. So first of all, I just raise C1 to the power of X. And C1, if you remember, here is G to the power of Y. That's why instead of C1, I just put G to the power of Y. Then I raise it to the power of X. This term over here can be written, I can switch the power, so g to the power of x to the power of y, but g to the power of x is basically my age. Okay, so instead of this guy, I'm writing h to the power of y, but h to the power of y is my s over here, so I'm getting the variable s. Now I'm finding its multiplicative inverse. If you remember, multiplicative inverse means that if I multiply s with s to the power of minus 1, I should get 1. Then do the following. I take C2 and multiplied with s to the power of -1. But C2, if you remember, is m multiplied by s, so I'm just substituting for that, and then multiplying with s minus 1. S multiplied by s minus 1 is 1, so I'm getting m multiplied by 1, and m multiplied by 1 is m, which is the original message over here. So this is how it works. Now, why
Mr. Akrim,
yes?
you still have more of 5 minutes.
Okay, I just go briefly. Thank you for reminding me. Okay, so the homomorphic property tells me that if I multiply two ciphertexts, I basically am going to get a multiplication and encryption of those ciphertexts multiplied. Okay, so if I multiply encryption of M1 and encryption of M2, I'm going to get this stuff, this part over here. Now, there are other cryptosystems. Maybe here, if you didn't understood the method what I was talking about, maybe this is going to help you. So if I have 4, these are from last year's slides, basically I'm encrypting. There's the FV and BGV schemes. If I encrypt 4 and I get this ciphertext, and 7 I get this ciphertext, and if I add the ciphertext, I'm going to get another ciphertext which encrypts 11. Similarly, it happens with multiplication. Okay. The Chinese remainder theorem enables me under one ciphertext to encrypt multiple integers. So if I add A and B, it's like component-wise adding those guys. And if I multiply A and B, I multiply multiple guys in one turn at the same time. Now, this is some homomorphic cryptosystems. Now let's go with the applications of homomorphic encryption. Privacy preserving findings. So someone has some incomes in his bank account and should pay taxes for that. Let's assume that the taxes are 20%, 0.2. What we are going to do, but those are private data. But anyway, we want to see whether there is tax evasion going on or not. How are we going to do that? We want to keep the privacy of the data and we want to see whether the guy has paid the taxes. Well, very simple. I'm just encrypting all of those guys in this manner. Now I have those guys encrypted. And then I'm adding the income. So I can do it by adding the ciphertext. Then after I get the income, I'm multiplying it with the tax added value. And I'm getting that it's this much. Furthermore, I just take B, which is the tax that should be paid, and I just compare A and B. How do I compare it? Well, I will subtract A and B. Okay, so total income is 10,000. When I multiply it by 0.2, which is the taxes, it's 10,000 multiplied by 0.2, it's 2,000. So the income is 2,000, and the tax that should be paid is 2,000, and the tax that the guy paid is 2,000. How do I know whether the guy has paid the taxes or not? Well, I just subtract A and B and multiply it with a random number. I can do it. If I get 0, when I decrypt the final result, that means the taxes are paid. Otherwise, they are not. For the genomics, so I'm just going to mention this part. If we have a lot of individuals and their genomes, maybe we can figure out something about the pandemic or diseases. But the problem is if we have the full genome of a certain individual, that can reveal sensitive private data such as fingerprints, biometric data, country, family origin, and so on. And we want to keep that private. So what do? We do the sequencing. So we are going to encode it in this manner. 1 for adenine, 2 for cytosine, 3 for guanine, and 4 for thymine. And then we are going to encrypt it and put it on the cloud. Now, if you're interested in part of data, we are just going to multiply with 1. So we are interested in this part of the genome. We are multiplying it. Everything else is 0. This is 1. And I get this part over here. Now, this is for one individual. If you want to check this part of the genome, of the genes, for multiple individuals, so this is for one individual, another individual, then I just do the following thing. Do secure comparison, which I already mentioned, and check whether they are differ from each other. And we see here that they differ in this part over here. Everything is held, so they differ over here. And I just say everything is the same except for this one. And I do it in privacy preserving fashion. Secure e-voting. Well, basically, voter 1, voters, if they want to vote for a certain candidate, they just put 1, otherwise they put 0, okay? And then I just sum up, and we want to keep it secure, okay? So it's explained over here. Maybe we can check it later on, and you can ask it during the QA section. Also, we can apply secure machine learning and data mining. We already explained it during the last year, so we're not going to do it over here. Secure machine learning can be done with deep learning as well as almost all of machine learning algorithms. Now let's conclude. Okay, so not only does homomorphic encryption provide an extra layer of defense due to encrypted data, but it's also a powerful tool in processing data while they are encrypted. So besides, finally, besides the real-world applications that we saw, homomorphic encryption can also be used in cryptocurrencies, in secure graph theory, in secure private scoring of databases, and so on. I thought I would finish in 20 minutes. If it's more than that, I apologize. And maybe you can ask questions during the QA session. Thank you very much.
Thank you very much, Mr. Archie. Yeah. It's very interesting topic. We need encryption when we always share our data in internet. So the next, okay?
Of course, yes, we need it.
Yeah. Next speaker is Mr. Nasir Farid.